Welcome everybody to the Simons Institute. My name is Sampath Kannan. I'm the Associate Director here. Some of you have heard this spiel about 20 times, but for people like Sanjeev, who hasn't heard it for a while, the Simons Institute was founded by a generous grant from the Simons Foundation in 2012. And they have funded us pretty much essentially up to this point, although we are in a new phase where we are looking for other sources of funding as well. But we are good to survive for at least another 10 years. So you should not worry immediately. And Simons Institute brings together, as you know, researchers at the top in theory from around the world, but also young stars of the future. We work on both, we have programs on both, internally focused on understanding the nature of computation itself, but often we have programs that look at other fields from an algorithmic lens. And this has been very successful. We've had programs, connect, of course, quantum computing that connects us to physics is a very strong program, a sequence of programs here, but we also have programs in econ and CS and social sciences and CS and so on. So one thing I want to say is that this workshop has been put together by a lot of people from outside. Chiefly Sanjeev, I think, is the main organizer here. So we thank all the organizers for doing this. A few sort of bookkeeping requests. One is that this auditorium, maybe to your surprise, does not permit any food or drink. And that's why we've not had to pay for upholstery for all these years that we've had it going. So please respect that rule. The other thing is that we have had a sequence of about 10 workshops here in the last 10 weeks without a break, and our staff cannot leave the building until everybody leaves the auditorium and the doors can be closed. So we request that as soon as the program is over for the day, you continue your discussion outside and not inside, so they can close up and leave. With that, let me hand off to Sanjeev and have a great workshop.
Thanks, Sampath. So I, along with my co-organizers, Arthur, SF, Merav, and Mohsen, warmly welcome all of you to this workshop. We have an exciting program that highlights a lot of recent results on sublinear graph simplification and also their applications to classical, distributed, dynamic, parallel, and sublinear algorithms. And I think collectively, the attendees of the workshop represent a really wide range of expertise. So it's our hope that this workshop will bring about new connections and collaborations. And throughout the program, you're going to see time marked for discussions and 15-minute slots marked for discussion. This is not anything structured. It's just time for informal discussions, either with the speakers in that session or just among ourselves. Okay. So with that, I think we are ready to start. And our first speaker is going to be Janani Sundaresan, who's going to tell us about an exciting new result about matching in dynamic streams. Okay.
I have this, so. I'm Janani. Thank you for the nice introduction and for inviting. No, I need to stand here. And for inviting me to this workshop. I'm going to talk about maximum matching in order log and passes in dynamic streams. This is joint work with my advisors, Separ Asadi, Sohail Benajad, Christian Conrad, and Kiran Naidu. And Christian and Separ are here. Sohail is not here. I'm going to start by defining a matching. You have a graph G with n vertices and m edges. And a matching is any subset of the edges, such that for every vertex, you have at most one edge incident to this vertex. And Matchings, now let me talk about the model of computation here. We're going to work with dynamic streams. Here, the vertices of the graph are already given to you, and the edges are not given outright. They're going to be given as a stream of insertions and deletions. So let's just go over a little bit of the stream. Some edge can be added, another edge is added, another edge is added, and after a while, the edges which have been added can be deleted also. And at the end of the stream, you get the complete graph you're working with. You don't have order of m space to store all these edge updates. You only have order of n polylog n space, and you want to process the graph in this limited space. And this stream of edges may be repeated multiple times for multiple passes also. So for the matching problem in dynamic streams, we have worked on them a lot. There are a lot of results here. I'm not going to go into details of all of these results. We're only going to be talking about a constant approximation for matching. And the main reason for this is, at least for matching, we can actually boost the approximation ratio. So if you have an algorithm for matching, which gets a constant approximation in p passes and s space, even for unweighted graphs, you can boost it to get 1 plus epsilon approximation for any epsilon. And this is true for weighted graphs. And the total blow up in the number of passes and space is only some epsilon factors. So you can deal with this. So the main question we're asking is, you have order of n polylog in space, often referred to as semi-streaming space, and you want a constant approximation ratio. And yes? Yeah.
You need that in both the passes and the space. Block the space a bit more, but
It's just you repeat the thing multiple times, yeah. And you repeat it parallelly also. Okay. So what is the number of passes you need to get a constant approximation in order of n polylog in space? So let's look at some prior work focused on this constant approximation. So a bunch of papers are able to get order log n over log n in the number of passes for this problem. Okay? And in terms of lower bounds, all we know is you can't do it in one pass. So here, if you have only order n log polylog in space and only one pass, this problem is not possible to solve. So now I'm going to talk about our results. We're able to improve this upper bound all the way to order log n by an exponential factor. And simultaneously, we're also improving this lower bound to log n as well, effectively closing this gap. So more specifically, we're saying that in order of n polylog in space, there is an algorithm for constant approximation of maximum matching, which uses only log n passes. And we're also saying that in the same space, for any constant, any constant c, any c approximation for this problem is going to need log n passes. Just a reminder, if you have this constant approximation, you can get any 1 plus epsilon approximation also for some constant epsilon. So any questions about this? Right. So this talk is going to be focused only on the upper bound result. The main reason for this is a sketching algorithm, and sketching is a general technique you use to simplify graphs and process them in limited space. Okay. So let's go over what sketching is. We have a choice to choose some sketch matrix, okay? And the dimensions of the sketch matrix are going to be some s times n choose 2. And let's look at the incidence vector of the edges. So this vector is indexed by pairs of vertices, and it's going to have 1 in that position if the edge exists, and 0 if it doesn't. If you multiply them, you're going to get the sketch of this graph. Okay? So you'll choose the sketch matrix so that the sketch is giving you all the relevant information you want for any graph. Okay? Yes?
what is the S again?
Yes, I'm going to talk about it. S is just the dimension or the size that you're working with. Okay, yes. So typically, S, you will choose it to be much less than n choose 2. And you're not going to store this sketch matrix explicitly. And the only thing you will store is the final sketch you get of this graph, which means if your sketch is doing what you want, you can actually just process this graph in O tilde of S space. Okay, this tilde is hiding log factors. So let's see how you would take this and translate it into the dynamic streaming setting we have. So if you have a sketch of your current graph, S times phi 1, okay, And then you take just the update vector, which is going to be like a +1 or a -1 in some specific edge, which is added or inserted. And then you just multiply them and add them. You're going to get a sketch of this updated graph too, which means you can find the sketch of the entire graph at the end of the stream in O tilde of S space. So what is adaptive sketching here in multiple rounds? If you're going to, you decide on something you want to do in the first round, and you design a sketch matrix for this. And then let's say you find the sketch of this graph for the first round. And after this, you're going to choose the next sketch based on your current sketch, right? So adaptively, you're choosing the next matrix. And then you continue for the next pass around, which means if you have some R round adaptive sketching algorithm, you're going to get an R pass streaming algorithm also. So in terms of sketching, this is our result. We're saying that in O tilde of n size sketches, again, hiding log factors, and out of log log n rounds, you can get an algorithm which gives you a constant approximation for matching. And like I said earlier, sketching is a general technique which you can use in multiple models as well. So one of the models it's applicable for is the MPC model. I'm not going to go into the details of this model, but then here, if you just take our sketching algorithm and put it in, you're going to get an algorithm which machines of O tilde of n memory and O tilde of n working memory in order log log n rounds. So this kind of parameters are not new. This is for, again, a constant approximation of matching. And all of these results are able to get this. But the difference is these results are not sketching algorithms, and they're typically using more than O tilde of n working memory for these machines. And with our algorithm, you can just get a simple sketching algorithm with just O tilde of n working memory for this setting as well. I'm going to talk about our techniques now. So just a one-phrase summary of this is both algorithms and lower bounds for this are obtained by just exploiting connections between the matching problem and maximal independent sets. So this maximal independent sets is something we're going to be using a lot throughout this talk. So I'm going to talk about it briefly for a little bit. A maximal independent set is any independent set of the graph which is not a proper subset of some other independent set. The red vertices here form a maximal independent set. Any other vertex has at least one edge to these red vertices, so you can't add them. Finding these, I'm just going to call it MIS. Finding these MIS is actually an easy problem in a lot of settings. So this is a simple algorithm which actually finds any MIS at the end. So let's just say you're going to start with some arbitrary ordering of the vertices. And you take the first vertex in this ordering and add it to the MIS. And then you're just going to remove all the neighbors of this vertex and the edges incident to this vertex. And then you just focus on the remaining graph now and do the same thing again. So this red one is the first vertex now. You're going to add it, and then you remove its neighbor, and then you're going to add this one, and then add this one. So you get these 4 vertices in your MIS. So this is a simple, nice algorithm. Now, instead of an arbitrary ordering, let's say we try a random ordering of the vertices. Okay? So this algorithm has been widely studied before, and we know a lot of nice properties for it. So one such nice thing about this is you can implement this algorithm in order log log n passes in O tilde of n space in seeming also. So this is a result by Arndt, Cormod, Guha, McGregor, and Wood in 2015. And recently, we showed that this dependence on the number of passes is tight, in the sense that if you want to find any maximal independent set, you do need omega of log log n passes. So let's go back to our results and connect these things to matchings. So we have this algorithm for finding MIS in order log log n passes by Arndt et al. And we crucially use this algorithm to get our upper bound for matchings also in dynamic streams. And we developed a lot of tools to be able to prove this omega of log log n lower bound for the MIS problem. And a lot of these tools, again, going to the omega of log log n lower bound we got for dynamic streams in matching. So just one thing I want to bring your attention to, this result was focused on the insertion only streams, which is typically easier. And we were able to extend this lower bound to dynamic streams now. So for the rest of the talk, I'm going to talk about fractional matching and vertex cover. Okay. After this, we're done with the summary of the techniques. Let's just move into the actual techniques. And then I'm going to talk about existing connection. Yes. Yeah. Yes. Okay. So this is focused for matchings, and in insertion-only streams, constant approximation for matching is easy anyway. Right? So it's just only the tools we use. The lower bounds don't really translate directly or anything like that. Okay. So yes, I'm going to talk about fractional matching and vertex cover, and then I'm going to talk about the connections we already know to the MIS problem, and then I'm going to talk about our reduction and briefly talk about some implementation aspects. So let's start with fractional matching and vertex cover. So here, in the fractional matching problem, you have an edge weight for every edge between 0 and 1, and you want to maximize the sum of these weights. And we want to obey this constraint that for all the vertices, the total sum of the weights incident on this vertex is going to be at most 1. So this is the fractional matching linear program. So the nice thing is, if you have a fractional matching in streaming, you're able to get a constant approximation for integral matching also. If you just sample these vertices independently with some extra blow up in order log n, and then you get these sampled edges, you can find an integral matching with these sampled edges. And this is going to be a constant approximation. So one thing here is this LP definitely has an integrality gap, but this integrality gap is just handled by this constant factor. And the dual of, So after this, we're going to only try to find a fractional matching. Okay? We're not going to be focused on an integral matching because you get the integral matching for free. Okay. So let's talk about the dual of this fractional matching problem, which is the vertex cover. Now, vertices have weights between 0 and 1, and you want to minimize the sum of these weights. And what you want to do is for all the edges, you want to say that the sum of the weights incident on this edge is at least 1. Okay? And this is the dual of the fractional matching LP we just saw. So now that I've defined these things, we can talk about the connections to the MIS problem. Well, one obvious connection is that every edge is going to have at least one endpoint in the complement of the MIS. So any MIS you take, its complement is going to be vertex cover. And this isn't even an integral vertex cover. There's no vertex weights or anything like that. The question we want to ask now is, how good a vertex cover do you get? And typically, you don't really get good vertex covers just by doing this. Right? If you have this graph, this is a minimum vertex cover, the blue vertices. But then if you take this MIS of the red vertices, you're adding all these blue vertices as the complement, right? And this gap can be very large. Okay. So we spoke about the random greedy MIS algorithm earlier, and we said it has a lot of nice properties. So let's take that algorithm and find its complement and see what we can do. So NA12 proved this very nice result in this year, saying that if you take the random greedy MIS and then find its complement, you're going to get a 2 approximate vertex cover in expectation. And you do get a good vertex cover if you do this. So yeah, let's go back to the MIS algorithm. What we did was just pick the random ordering of the vertices, add the first vertex in this ordering to your MIS, and then remove its edges, remove its neighbors and their edges, just repeat it among the remaining graph. So instead of just removing it, we're just going to take the complement and add the neighbors to the vertex cover. And NA12 proved that this algorithm actually gives a 2 approximation for vertex cover in expectation. We do know a lot of algorithms which give you a 2 approximate vertex cover, and this is just one entirely new one. And this proof is by an application of LP duality. We're going to look at some brief aspects of this proof, not going into too much detail on it. Yeah, so it is going to be useful for us. Okay? We're going to focus on the edges which send vertices to vertex cover. By that, let me be a bit more clear as to what I mean here. So if you have this graph, you're starting with this vertex and adding it to your MIS. And this vertex is now going into the vertex cover. And this is the edge which is responsible for sending it, the darkened one. Okay? And if you do the next neighbor, you get this edge which is responsible for sending it. You repeat this, you get this edge, and finally you get this edge. So if you take the entire process, you're going to get these 4 edges which send the vertices to vertex cover. And these edges can actually depend on the random ordering a lot. So the random ordering we started with, you get these 4 edges. In the next random ordering, you can get something very different. And in some other random ordering, again, you can get something very different. So let's just take all these random orderings and look at them together. Right? And well defines this probability for an edge, PE. This is the probability that an edge becomes one of these dark edges and sends a vertex to the vertex cover. And one easy thing to observe is that the expected size of the vertex cover from this algorithm is the sum of these PE values. Because in every run, each edge was sending only one vertex to the vertex cover. So in all of these things, you have 4 vertices in the vertex cover, and you have 4 of the darkened edges. So well proved that if you take these PE values and then take XC as PE over 2, this actually satisfies the fractional matching LP we had. I'm not going to go into a proof of this. It's very clean and nice, but yeah. So which means now we have a vertex cover matching pair, which is a factor 2 from each other. So you can say that this is actually a 2 approximate vertex cover. So it's from the proof of this paper, you do get a fractional matching also. So why can we not do this? It seems like we get a fractional matching as well, just from the MIS algorithm or the proof of this paper. So just find the MIS using the Ahn et al. Paper in order log log and passes. Okay? And then you focus on these edges, which are sending some things to vertex cover. And then you repeat them some log n times just to get a blow up. And each edge is going to be sampled here with some 2 times the edge weight you want in the matching. And then just try to find a large matching inside this. So earlier we said that if you just sample according to a fractional matching, you do get a constant approximation, and which is what we wanted. Does someone see why this doesn't work? Well, I don't know, yeah. The main issue here is the sampling process from the MIS algorithm is not independent. So let's look at an example run of this to see what goes wrong. Yeah. So this algorithm actually does the random greedy MIS. It finds it automatically. It's already there. Okay, so if you start with this graph, and this red vertex is the first in the ordering, then you're going to get these 4 edges. And if this vertex was the next, you're going to get these 4 edges. So you can just see that these edges don't really look like a matching, right? So what you end up getting from these edges are just a bunch of stars. The sampling process here is not independent, so you can't use it directly. Any questions about this? Yeah, okay. Now I'm going to talk about our reduction to maximal independent set. The main thing here was in the previous connection we saw, you looked at all these random orderings together to get a fractional matching. Now what we're going to do is try to get a fractional matching just from one run of this random greedy MIS. So this is in short, what goes on. Whenever some vertex goes to the vertex cover, you focus on the edges it has to the remaining part of the graph. So when some vertex u goes to the vertex cover, you're going to add a mass of 1 over the degree to the edges between u and the graph which is left. So this is not the final reduction, but we can just go with this assumption for now. We'll talk about the final reduction later. So if this is the vertex that is going to the MIS, then its neighbors are going to the vertex cover. And this one has a degree of 4. So you're going to add 1 over 4 mass to all these edges. And this one has only a degree of 1. So you're just going to add a mass of 1 on this edge. And after this, this is the remaining graph, all the orange vertices. Let's say this one goes to the MIS. And this one should go to the vertex cover because of it. It has a degree of 3. So you're adding a mass of 1 over 3 to all its incident edges. And lastly, these 2 are the remaining, these 3 vertices are the remaining graph. And you're going to add a mass of 1 on this edge. So after you do this, you're going to get these edge weights. And we're trying to find a fractional matching. So let's see what happens. It's obvious to see that we don't actually satisfy this LP directly with some large value just by looking at this vertex. It's violating this vertex constraint. except we only wanted an approximate matching anyway, so it's okay if you satisfy this by some constant factor. So if you have this, you can scale it back and still get a constant approximation, right? And what you want to see is check that the value we add to these edges is large, and each vertex, the weight you add is not too much. Let's just look at the value first. This is very simple to observe. Every time you add a vertex to the vertex cover, the total weight you add to the matching is 1. Okay? Because you're adding 1 over degree of u to degree of u many vertices or edges. Okay, so you're going to add 1 over 4 to all these 4 edges here. And so based on this, you can see that the fractional matching value is the same as the size of the vertex cover you're getting. And since any vertex cover is larger than the maximum matching, you do get that this size is larger than the maximum matching as well. Again, this is not true in the final reduction we do, but for now, let's just go with this. So this is the harder constraint to analyze. Why is this going to be close or to matching? So let's look at the source of mass for any vertex. When this vertex moves to the vertex cover or MIS, it's adding some mass to itself. And this value is exactly 1 as we just saw. Okay? So it doesn't add too much. But this is this part it may add too much, because observe that when the blue vertex goes to the vertex cover, it is adding a mass of 1 over 4 to the green vertex also. Right? And it's coming from its neighbors. All of your neighbors can add some mass to you. So the main observation here to bound this mass is that if some vertex, if we expect it to actually receive a lot of mass in some iteration, then we're expecting this vertex to actually get removed also in that iteration. So if you're going to get a lot of mass, then what may happen is you're actually going to be removed also after getting this much mass. So let's see why this is true. Since we're choosing a random ordering, any vertex being chosen to be in the MIS happens with 1 over n probability. So if this happens, then yes, it's going to be removed. Or if one of your neighbors is chosen to be in the MIS, then you go to the vertex cover and you get removed. So this happens with degree of this u vertex over n probability, because there are degree of u many vertices. So the total probability that some vertex is removed is some degree of u plus 1 over n. Now let's look at what is the potential mass you may get from your neighbors. So if your neighbor V was going to the vertex cover, because some of its neighbors got added to the MIS, it's going to add a mass on this UV edge. So probability of some neighbor being sent to the vertex cover is going to be some degree of V over n. We just saw this. So if this happens, the mass you add across edge UV is 1 over degree of V. So in expectation, you get like 1 over n mass from this edge. And the total expected mass is going to be degree of u over n, because there are degree of u many edges. So what are we getting here? For any iteration, the total expected mass you get from your neighbors is going to be upper bounded by the probability that you get removed completely from the graph in this iteration. Okay, so this actually gives us some potential to bound this mass. I'm going to look at this away from a graph theoretic sense and just put it as a game of random variables. It is a bit of a mouthful, but I want to call it the gain a lot, then get out game. Okay? So xi is going to be the mass gained by some vertex u at some iteration I. And you have n random variables because there are at most n iterations. And what you're saying is, conditioned on any previous choice of the random variables, expected value of this random variable xi is less than the probability that all the later random variables become 0. You're not in the graph anymore. So if you have such a construct, what we want to do is bound the expectation of the sum of these random variables to be some constant. So this is like the total mass that a vertex gains. And the variance of this sum to be some constant times expectation also. So if you do this, you can use Chebyshev carefully to actually bound like the total mass that each vertex gains. So unfortunately, just from what we have, this does not end up happening. So let's look at this graph. And we're trying to bound the mass on U. If this red vertex was chosen to be the MIS, it's going to send all these vertices to the vertex cover. and it's going to add a mass of half to all these edges. So with probability 1 by n, the mass received by this u vertex is going to be n over 2. So in expectation, you can say that the total mass is still going to be constant even for this example. But then the variance of this mass is going to be around n here, which means what we wanted does not end up happening. So what we want is an absolute bound on each of these xi values first to be able to get a bound on the variance as well. This is our final reduction. We're going to add a mass of 1 over degree of u only to the lower degree neighbors of u in the graph. So if the red vertex was going to the MIS and the blue vertex was going to the vertex cover, it does have 3 vertices or 3 edges. So it would have added 1 over 3 mass on all the edges. But then since the degree of this vertex is 4, it's not going to add anything here, and it's not going to add anything here as well. So why does this give you an absolute bound on the random variables? So it's easy to see that if V vertex was adding some mass on the UV edge, it's only going to do it if the degree of U is less than that of V. Which means any mass you add, which is 1 over degree of V, is at most 1 over degree of U as well. And you have only degree of U many edges here, so the total mass is at most 1 in each iteration. Let's go back to the game. Now you have this extra condition that each of these xi's is bounded, and this is actually enough for you. You can bound the expectation of the sum of these variables to be some constant, and the variance also to be some constant times the expectation. But then what may end up happening is we don't actually add as much value as we did to the fractional matching as before. Right? Earlier we had that the value of this fractional matching is the same as the size of the vertex cover. This is not going to be true now. What we get is that this is still half the size of the vertex cover in expectation. I'm not going to talk about why this is true either. It works, yeah, sorry. Let's go back to the fractional matching LP we had. So these are the final things that we get. We're able to get these XE values, and the total value of this matching is half the size of the vertex cover. And for all the vertices, you're getting that the total weight added to these vertices is upper bounded by some constant. And we satisfy the LP on the right with some large value in expectation. Yes?
What's the threshold?
There's no threshold. It's just everything with lower degree you add it. Everything with just like the degree lesser than you add it. Otherwise, you don't. Okay. So I'm going to talk about some briefly talk about some challenges of implementing this reduction. The Ahn et al. Paper that we had for the random greedy MIS only needed to look at just the neighborhood of this vertex U when you add it to the MIS to figure out which vertices you want to remove. It's only focused on finding the MIS. But in our reduction, we're adding a mass to the 2 neighborhood of U also, because when vertex V goes to the vertex cover, it's adding some mass to the VW edge. And it's not really clear how to get this 2 neighborhood right now with the Ahn et al. Algorithm, but we are giving a new algorithm to get this 2 neighborhood as well. This algorithm it's slightly adjacent to the reduction, so I'm not going to talk about this either. Now, we still need this check that it's only adding a mass to the lower degree neighbors, right? It's not going to add a mass of all the neighbors. But then this check to see that, at the point you're getting removed, what are your lower degree neighbors? This is something we're not able to get. And even information theoretically, this information may become too much to store because you need to store for every edge, which is the lower degree neighbor every time the edge gets removed. So this is what we end up doing. You're going to sample all the edges in the 2 neighborhood of this vertex when it is added to the MIS with roughly the same value. And notice what is happening here. Previously, this was adding a value of only 0 to the edge, but now you're sampling it with a higher probability. which means since you're sampling more edges, then you still get a fractional matching from the sampled edges. This is okay. You can do this. But it may be possible that since you're sampling more edges, you may actually violate the space constraints you have and sample too many edges also. But then each vertex was only going to add like one mass totally over to the fractional matching, and roughly it's still going to sample only order log n edges by itself. So you don't violate your space constraints. And that's it. I'm going to conclude now. So we gave a reduction from the random greedy MIS algorithm to a constant approximation of maximum matching. So this reduction was inspired by the algorithm of Welt, which gave a reduction to vertex cover, and we're able to generalize this to matchings as well. And this reduction, we're implementing it as a sketching algorithm, and this gives you a constant approximation of matching in log n rounds with O tilde of n size sketches. And as our final result, we're saying that the pass complexity of 1 plus epsilon approximation of maximum matching for any constant epsilon in dynamic streams is, if you have order of n polylog in space, is theta of log n. And this is obtained by exploiting connections to maximal independent sets. And we're improving both the upper bound and the lower bound simultaneously. So what are some open questions here? The main thing, well, slightly adjacent question, is what exact dependence on epsilon do you get for this 1 plus epsilon approximation? We don't understand this well, even in the case of insertion-only streams or simple graphs like bipartite graphs. And there has been a long line of work trying to better this dependence and better understand it. And we also had a lot of connections to the MPC model. So can you get better upper bounds or some conditional lower bounds for this model as well? Thank you. Yes. Yeah.
So I'm curious about, because you're saying about the sketching algorithm, but I didn't see the sketching metric that you mentioned here. Did you help me or?
Yeah, I think, so the only way we access these graphs is through sparse recovery, right? And for sparse recovery, we already know like a lot of sketching matrices would do it, like the Van der Waals matrix and things like that. So the only thing we need is sparse recovery, and we're able to get that just through the sketching.
So about the result, so in the end, do you get an expectation result? Or do you get
No. What you can do is you can do some vertex sampling approach to reduce it to this expectation thing, and you can use some averaging argument to bound that. So you can get like a constant approximation with high probability. The result is with high probability.
So if you wanted to just estimate the size of the matching in a dynamic stream, what's known?
Unfortunately, I think even for one pass, we don't know the complete results for this. I don't remember the exact bounds we get. Even in one pass, I think lower bound is still. Okay, no, I can't tell you the exact things, but I know that the question is still open for one pass. Yeah.
So can you say a little bit more about this thing? So are you using the Anand et al. Result as a black box? Or
No.
It's completely opened up.
Yeah, it is completely opened up. Yeah.
And this adaptive nature of the sketch that you're developing is sort of mimicking their process, but somehow what's adapting is changing over?
Yeah, okay. So the main difference, as I said earlier, was that you want the two neighborhood of the vertices you're adding to the MIS. So based on that, after every pass, what the Anand et al. Paper does is just batch these random permutations together and take like a fixed size of these permutation vertices at every pass and process those. So what we wanted was just to check whether in the Anand et al. Paper, if you want to figure out if some vertex goes to the vertex cover, after you're done with like some specific process, then you can just see, okay, you know what, let me just count if this has any edges to the MIS or not. And then if it has some positive edge to the MIS, then it's going to the vertex cover. Here, we wanted the actual exact neighbor which is going to the MIS, and we needed some extra algorithms for it. So we cannot use it as a black box. The main adaptive nature is to just, at the end of every pass, you figure out what goes to the MIS, what goes to the vertex cover, and then you decide what to do next. Any other questions?
I don't know if you talk about it, but how about exact matching? Like,
unfortunately, even that is completely open, even in insertion-only streams. The best lower bound we know is omega of some log n passes. in semi-streaming. And the upper ones are like n raised to 3/4 number of passes. And we don't have anything to do here. We don't know what to do here. Yeah. Anything else?
Sorry, Dr. Long is entered the 3/4.
I think so, yeah.
Okay, let's thank Janani.
Thank you so much.